Beneath the calm surface of Earth's oceans lies something far more unforgiving than darkness. A drop so sheer that the seafloor plunges nearly 11,000 meters straight down into fatal pressure where even hardened steel can fail. For decades, scientists and explorers have tried to navigate these most extreme vertical descents, facing physical forces that would collapse a submarine in an instant. If the idea that a single miscalculation could mean total erasure at the bottom of the hadal zone unsettles you, you're not alone. We're about to trace how humans learn to survive a fall almost no machine can guarantee, and why our understanding of the deep still feels terrifyingly incomplete. The surface of the ocean covers more than 70% of our planet, a blue expanse that seems gentle enough to cross in a single day. But beneath that calm, the seafloor can vanish almost straight down, falling away for 10 vertical kilometers into a realm beyond sunlight, beyond rescue, and beyond most human imagining. This is the hadal zone, a name borrowed from Hades, the world of the dead, a territory defined not by distance from shore, but by the sheer drop-off, where the oceanic crust buckles and sinks under tectonic pressure. Here, starting at 6,000 meters and plunging nearly twice as deep, the ocean becomes a vertical wall, an open wound in the planet's crust. To picture the scale, imagine standing at sea level and looking up at Mount Everest. Now imagine that same mountain inverted and still coming up short. Challenger, the planet's deepest known point, reaches nearly 11,000 meters down, farther than any mountain rises above the clouds. At these depths, the descent is not gradual. The seafloor can drop thousands of meters in the space of a few horizontal kilometers, forming trenches so steep and narrow that they have only recently been mapped with any confidence. Most of the world's ocean is much shallower, but these rare places, the deep trenches, are where the vertical dimension of Earth becomes absolute. For most of history, these depths were known only by numbers on a line, measured by weighted ropes and later by sonar echoes. The idea of actually seeing the abyss seemed impossible. In the early 1930s, zoologist William Beebe and engineer Otis Barton built a steel ball just big enough for two men, the bathysphere, and dangled it on a cable off Bermuda. In August 1934, they reached 923 meters, less than 1,000th of the ocean's volume, but still deeper than any human had gone. Beebe wrote of the darkness pressing in, of the cold, and of the sense that only a few centimeters of steel separated them from a world that did not care if they survived. Every descent was a calculated risk. One cable, no backup, no way to escape if the sphere jammed or a seal failed. Yet for the first time, humans saw living creatures in the deep, bioluminescent fish, jelly-like forms, and flashes of light that vanished before they could be named. Even that first glimpse was just the beginning. The true vertical drop, the one that runs from the surface to the hadal zone, remains almost untouched, a place where the margin for error shrinks to nothing. If you are drawn to calm, fact-driven journeys into places humans barely understand, consider subscribing. The descents only get darker, and the drop only gets steeper from here. Pressure in the ocean does not climb gently. With every 10 meters of descent, another full atmosphere of weight presses in. At the surface, a diver feels the same force as the air above us. 1 atmosphere. Drop to 100 meters, and the ocean multiplies that by 10. At 1,000 meters, the weight stacks up to 100 times what we know on land. By the time you reach the hadal trenches, 6,000 meters, 8,000 meters, 10,000 meters, pressure reaches levels that seem unreal, 1,000 atmospheres, or about 100 megapascals. That is the force of a family car pressing on every square centimeter. At these depths, the difference between survival and destruction is measured in millimeters. A weld that is too thin, a seal that compresses a fraction too much, or an O-ring with a hairline flaw. Any of these can be the single point where the ocean finds its way in. This is not a world that forgives mistakes. Hydrostatic pressure acts on every surface, every fitting, every cable. The engineering challenge is not just to build strong, but to build flawless. Metals that seem indestructible at the surface can deform, crack, or fatigue under repeated cycles of compression. Ceramics and glass, chosen for their strength, can shatter without warning if a flaw escapes inspection. Even the foam that provides buoyancy is at risk. Each tiny, hollow sphere inside it is squeezed by the surrounding water, and over time, the weakest ones collapse, changing the balance that keeps a vehicle afloat. Designers use titanium for its strength and resistance to corrosion, but even titanium must be perfectly formed, with every weld and joint verified and re-verified. The pressure does not simply increase, it multiplies every vulnerability. A window that is safe at 1,000 meters can craze or crack at 9,000. A cable gland that holds at the surface can be forced open by the relentless squeeze of the deep. The difference between a successful dive and catastrophic loss is often invisible until the moment of failure. In the hadal zone, the ocean is not just deep, it is actively hostile to anything that tries to enter. Every piece of equipment is tested in pressure chambers that mimic the crushing force of the trenches, but real dives still find new ways to expose the limits of material and design. The margin for error shrinks with every meter until it is no longer a buffer, but a razor's edge. This is the physics that governs every descent into the abyss, a world where the only certainty is that the ocean is waiting for the smallest mistake. January 23, 1960. The Bath Escape Trieste began its descent into the Mariana Trench, carrying Jacques Piccard and Don Walsh inside a steel sphere barely large enough for the two of them to sit shoulder to shoulder. As Trieste dropped past 9 kilometers, about 30,000 feet into the hadal darkness, a sudden, deafening bang echoed through the hull. For a moment, neither man could tell what had failed. Every gauge was checked in silence, every system scrutinized for signs of water or pressure loss. Only after the shock faded did they realize the source. The outer acrylic plug of one of their viewports had cracked under the immense load. At that depth, nearly 1,000 atmospheres pressed against every surface. The steel sphere and its inner seals held, but the acrylic, meant to provide a clear view of the outside world, had revealed a hidden weakness. There was no leak, no breach, just a violent reminder that even the smallest flaw can announce itself with no warning, and that the boundary between safety and disaster is measured in millimeters. The men had no way to step outside, no tools to repair what had broken, and no rescue waiting above. Their world was reduced to the cramped interior, the sound of the hull settling, and the knowledge that the ocean was still pressing in from every side. Despite the damage, Trieste continued its descent. Piccard and Walsh reached the seafloor at a depth of about 10,911 meters, where they spent just 20 minutes on the bottom, long enough to confirm that life existed even here, but never long enough to forget the risks. When they returned, the cracked viewport was inspected and logged, a testament to the razor-thin margin that separates survival from failure in the deep. The lesson would echo through every subsequent dive. In the hadal zone, even the hardest steel and the clearest window can hide the seeds of their own defeat. Nereus was built to do what no human body could survive. Descend alone to the deepest trenches, withstand 1,000 atmospheres, and return with data from the edge of the known world. Its design was a study in calculated risk, Instead of a single thick hull, Nereus carried dozens of small ceramic spheres, each one a pressure vessel for sensitive electronics, each engineered to endure the relentless squeeze of nearly 10 kilometers of water. Ceramic was chosen for its strength in compression, but at these depths, even the strongest materials become brittle. Every sphere, every joint, every length of syntactic foam was tested and retested. But the ocean does not care about test results. In May 2009, Nereus reached Challenger Deep, descending to about 10,902 meters. The vehicle sent back images and samples from a place so remote that sunlight and radio waves cannot reach it. For 5 years, Nereus operated at the frontier of hadal science, diving repeatedly into trenches few machines had ever touched. Each time, it crossed the invisible line where the margin for error shrinks to nothing. A world where a flaw smaller than a grain of sand can trigger disaster. On May 10, 2014, Nereus was nearly 10,000 meters down in the Kermadec Trench. Without warning, contact was lost. The ship waited for a signal, but none came. Hours later, fragments of syntactic foam and lightweight debris floated to the surface. The rest of Nereus was gone. Forensic analysis pointed to a catastrophic implosion, a sudden collapse of pressure housing under the weight of the ocean. No detailed cause was ever recovered. At that depth, the evidence is scattered and irretrievable. Engineers suspect a microscopic flaw in a ceramic sphere, or fatigue from repeated dives. But the truth is that the ocean found a weakness and erased the machine in an instant. Nereus was not the first uncrewed lander lost to the deep, and it will not be the last. In the hadal world, there are no partial failures, only total loss or improbable return. Each descent is a wager against physics, with no hope of rescue. The ocean keeps what it destroys, and every new design carries the memory of those that vanished before. When Deep-Sea Challenger slipped beneath the Pacific in 2012, it was not just another gamble with the abyss. James Cameron, alone in a vertical green torpedo, rode a machine built for a single purpose: to survive the pressure of nearly 11,000 meters of water. The pilot's world shrank to a titanium sphere, just over 1 meter across, walls nearly as thick as a man's arm, engineered to flex but never crack. Every system was doubled or tripled: redundant oxygen, CO2 scrubbers, battery backups, ballast releases, each checked by hand and by sensor every few hundred meters down. The descent took hours, with the sub's foam-packed body resisting the squeeze of 1,000 atmospheres. At the bottom, Cameron spent more than 2 hours on the seafloor, longer than any human before him at that depth, collecting samples and film. When he surfaced, Deep-Sea Challenger became both a technical milestone and a private project, with its data and design details entering the scientific community only after careful review. 6 years later, the 5 Deeps expedition set out to make the deep ocean accessible not just once, but again and again. Victor Vescovo piloted the DSV limiting factor, a titanium sphere rated for full ocean depth, certified by DNV for commercial repeat use. Inside, the pressure never changed: 1 atmosphere, shirt sleeves, life support steady. Outside, the hull endured the crush of more than 1,000 times surface pressure every dive. Limiting factors engineering was built for cycles, repeated descents, each time trusting welds, seals, and the geometry of the sphere. Ballast was released in careful stages, buoyancy fine-tuned by syntactic foam designed to resist crushing. On one dive to Challenger Deep in April 2019, Vescovo and co-pilot Hamish Harding spent 4 hours and 15 minutes at the bottom, mapping, sampling, and proving that these depths could be reached safely, not as a stunt, but as a routine operation. Where earlier dives were one-off, modern submersibles made the abyss a place for return visits. The confidence did not come from luck, but from layers of engineering. Titanium that bends but does not break. Life support with backups for every backup, and a discipline of checklists that treats every dive as if the ocean is waiting for the smallest oversight. In the hadal world, control is never absolute. But for the first time, human descents became less about survival and more about what could be discovered on the next dive. Challenger Deep is not alone. The Pacific hides other trenches, each a steep descent, each challenging the Mariana's claim to singularity. Horizon Deep, at the southern edge of the Tonga Trench, is measured near 10,823 meters. The Emden Deep in the Philippine Trench reaches over 10,500 meters. The Kuril-Kamchatka Trench, stretching off Russia and Japan, edges close to these depths as well. These figures are not fixed. Every reading depends on the survey, the equipment, and the restless sea. Multi-beam sonar, the tool of choice, sweeps wide areas but leaves gaps where a sharp depression might hide. A slight miscalculation in sound speed shifts results by meters. Storms and heavy swell add another layer of uncertainty, making depth a moving target rather than a settled fact. Logistics shape the challenge as much as the numbers. Horizon Deep sits far from any port, battered by storms that can halt work for weeks. The Philippine Trench is fractured by earthquakes and landslides, while the Kuril-Kamchatka Trench faces subarctic gales and incomplete maps. In 2019, Victor Vescovo piloted the limiting factor to Horizon Deep's floor, confirming its depth firsthand. Each descent into these rival trenches is a test of patience and precision, where the numbers never quite settle and the unknown remains just out of reach. At the very bottom, where pressure flattens steel and sunlight is a memory, life persists in forms that seem to defy the rules of biology. Hadal amphipods, small shrimp-like scavengers, have been collected from the deepest trenches. Their cells are loaded with TMAO, a molecule that stabilizes proteins against crushing pressure, allowing them to function where most life would unravel. Snailfish, pale and nearly translucent, glide along the trench floor at depths beyond 8,000 meters. Their bodies adapted to resist the squeeze that would burst an ordinary cell. Cameras baited with mackerel have captured these fish in high definition, revealing a world that is active, not empty. Yet every sample, every image, tells a second story. Chemical assays of amphipods from the Mariana and Kermadec trenches have detected persistent pollutants, PCBs, at concentrations up to 2 nanograms per gram, levels that rival or exceed those found in industrialized coastal waters. Microplastics and synthetic fibers have been found in the guts of trench organisms, proof that human debris rides ocean currents into the planet's deepest vaults. Even here, in a place that should be untouchable, the evidence of our presence is unmistakable. Life adapts, but the Hadal Zone is no longer a world apart. It is both a refuge for the most extreme survivors and a silent archive of everything that falls from above. Hadal trenches carve less than 2% of the seafloor, yet they hold outsized power over the planet's future. These are not just deep scars. They are the front lines of tectonic subduction, where oceanic crust is pulled beneath continents, driving earthquakes and volcanic arcs. Each trench acts as a conveyor, funneling sediments and organic matter into the Earth's interior. In these narrow, steep corridors, carbon-rich debris rains down and is buried at rates far higher than on the flat, abyssal plains. Per square meter, some trench floors lock away organic carbon 10 times faster than the surrounding deep sea. Globally, that means trenches account for just a few percent of all marine carbon burial each year. A small fraction, but in a climate system balanced on tight margins, even these hidden flows matter. Every submersible that dares the abyss is built under rules drawn by classification societies, organizations like DNVA that set strict standards for hull strength, safety margins, and proof testing. There is no single blueprint. Some engineers favor redundancy, even proposing nested spheres to guard against failure. But the ocean sets the final terms. Regulations demand that hulls withstand pressures well beyond their design depth, with safety factors that leave no room for wishful thinking. Still, the ocean's patience outlasts any certification. Materials age, micro cracks grow, and the smallest oversight can become a fatal flaw. Autonomous vehicles and swarms of robotic landers may soon map and sample these trenches with new precision, but the risk remains absolute. The deep does not negotiate. It allows us to visit, to measure, and to wonder, but never to control. Right now, less than 0.2% of the ocean floor has been explored in detail, and even our most advanced vehicles can only visit the hadal trenches for hours at a time. As new technology pushes deeper, the risks and unknowns only multiply. The ocean's vertical extremes remind us some frontiers remain indifferent to mastery. The planet's deepest places still decide what secrets, if any, we're allowed to bring back.